In this video, we're going to continue our discussion of self-type by talking about the type-level operations that are available on self-type. And this will help to clarify what self-type actually is and its role in the type system. So let's begin by thinking about the example that we discussed last time. And if you've forgotten what that is, let me just write it down quickly. We had a class called count. And count had one field, an integer I, that was initialized to 0. And it had one method called inc that returned something of type self-type. And all inc did was to increment the counter field and return the self object. And I've probably made some syntax errors here, but that's not really important. That's the basic code for the count class. And the question is, what can be the dynamic type of the object that's actually returned by inc? And the answer here is that it could be whatever is the type of the self object, whatever is the dynamic type of the self object. And if we think about a big program where there's multiple classes that inherit from count, then the answer is that inc could return count or any subclass of count. So it's going to return something that's at least at most count, but it could return something more specific. The dynamic type could be something more specific. It could be a subclass of count or a subclass of a subclass of count. Anything that inherits directly or indirectly from count is a possibility. So what's the general case? Well, let's think about a class C. And in this class C, there's some expression buried somewhere inside of it that has the type self-type. And it doesn't really matter how that expression got the type self-type or what it is. Let's just say that it has that type somehow. Well, what are the possible dynamic types of the expression E? And from our discussion on the previous slide, it seems clear that the dynamic type of E, when you run E, you're going to get back something that's a subtype of the class C, the enclosing class in which the self-type appears. And that's interesting because it shows us that the meaning of self-type actually depends on the context. So what this self-type means a subtype of the class C. If I had written self-type in a class D, somewhere in the definition of class D, there it would mean a subtype of the class D. And so to remind ourselves what class we're talking about, what enclosing class we're talking about, we're going to subscript occurrences of self-type with a class name. So self-type sub C here is going to refer to a syntactic occurrence of the keyword self-type in the body of the class C. And this also suggests a very simple typing rule, and really the first useful fact about self-type, which is that self-type sub C is a subtype of C. And this is really a key idea here, that a self-type in class C is some subtype of the class C, because this also helps illustrate what self-type really is. The best way to think of an occurrence of self-type is that it's a type variable that ranges over all the subclasses of the class in which it appears. So self-type sub C you should think of as a type variable. It's something, it doesn't have a fixed type, but it's guaranteed to be some type bounded by C. So it's going to be only one of the classes that inherits directly or indirectly from the class C. Now that rule, that self-type sub C is a subtype of the class C, has an important consequence. It means that when we're doing type checking with self-type, it is always safe to replace self-type sub C by C. So it's okay to promote any self-type sub C, which could be C or a subtype of C, to say, okay, we're just going to say that it's C. All right. And that suggests one way to handle self-type, which is just to replace all the occurrences of self-type sub C by C. Now, unfortunately, that turns out not to be very useful. It's sound, it's correct to do that, but that's really just like not having self-type at all. That's as if we went back to the example we did in the last video where we started out without self-type and we found out we couldn't use inheritance in the way we expected. So to do better than just throwing all the self-types away, we need to incorporate self-type into the type system. And the way we're going to do that is by looking at the operations that work on types in the type system, and there are two of them. There's the subtype relationship that we've talked about before, so when one type is a subtype of another, and there's the least upper bound operation that tells us what the smallest type is that's bigger than both of two argument types. And all we have to do, or what we're going to do now, is extend these operations to handle the type self-type. So let's begin with the subtype relationship, and in our definition here we're going to use some types T and T prime, and these are just normal class names. They are any class names, but not self-type. So one possibility is that we have self-type on both sides of our subtype relationship, and in that case it's easy to see that self-type sub C should be a subtype of self-type sub C. So to convince yourself of this, think of self-type again as a variable. And we can plug in for that variable any subtype of C. But just like variables in algebra, if we plug in one particular class for an occurrence of this variable, we have to pick the same one for every occurrence of the variable. So in particular, if we pick some subclass A of C, then we wind up with A is a subtype of A. If we plug in A for both sides, we can see that the relationship holds. Similarly, C is a subtype of C. And for any other subtype we might pick, if we bind the variable to that subtype, we can see that this relationship will be true. Now, another thing you might think is, well, what if the self-type sub C is compared with self-type from another class, say self-type sub D? And it turns out that in the cool type rules, this will just never come up. The cool type rules are written in such a way that we never need to compare self-types from different classes. And I haven't shown you that that's the case yet, but when we actually go through the type rules for self-type, you'll see that it's true. Now, another possibility is that we have self-type on one side and then a regular type on the other side. So when is self-type sub C a subtype of T? Well, we're going to say that that's true if C is a subtype of T. And here we're using our rule that it's always safe to replace self-type by the class that indexes it. So in this case, since C is a supertype of anything that self-type sub C could be, clearly if C is a subtype of T, if T is at least C or possibly something higher in the class hierarchy, then T will be a supertype of anything that self-type sub C could stand for. Another case is when we have a regular class name on the left-hand side of the subtyping relationship and self-type on the right-hand side. And in this case, it turns out we have to say that this relationship is false, that T is never, a regular class name is never a subtype of self-type sub C. And to see this, just think about the possibilities. So where could C and T be in the type hierarchy? So if T and C are unrelated, if they are inherit from object and they have nothing to do with each other, well then clearly T can't be a subtype of self-type sub C. They're just two unrelated classes. So the only way that this could possibly work out is if they're related somehow. Now if T is a subtype of C, well then you might think that this could work out. But it turns out that we can't allow it even in that case. And here's the reason why. Think about a hierarchy where T has some subclass. Let's just say that it has a subclass A. And now, because self-type sub C ranges over all the possible subtypes of C, we could plug in A here, and T is not a subtype of A. They're in the wrong relationship. And so because it doesn't work for all the possible values of subtype sub C, we can't say that this is true. We have to say that it is false. Now, there is one very special case where one could argue that we should allow this to be true. And that is in the case where T is actually a leaf of the class hierarchy. And let me actually draw this a little bit differently, just to emphasize this. Let's say that C is a class up here, and then T, through some chain of inheritance relationships, is a subtype of C. So it's not immediate, but there might be other classes in between. Just to emphasize, this relationship doesn't have to be immediate inheritance. It could be transitive inheritance. And now if T is a leaf of the hierarchy, and it is the only leaf of C, if C has no other subclasses, then in fact T is a subtype of self-type sub C because it is the unique minimal type that is in the subtype hierarchy of C. But the problem is that this is extremely fragile and doesn't work if you modify the program. In particular, a programmer might come along and add some class A over here that's unrelated to T, but is also a subclass of C. And now this would no longer work, because if I plug in A for self-type sub C, then I see that T is not a subtype of A. All right, so we could allow it in the very special case that C had only a chain of inheritance, not a general tree under it, and that T was the leaf of that chain. But that is so fragile to future program extensions, and if you broke it by adding another class over here, all of a sudden you would get type errors in pieces of code that had previously been type checked to work and hadn't changed at all. It just wouldn't be a very nice language design. So, to summarize, T is never a subtype of self-types of C. And finally, if we're comparing two normal types with not self-type, then we just use the rules that we gave before. So the subtyping rules we had for normal class names haven't changed at all. And that covers all four cases. We could have self-type on both sides, we could have self-type just on the left side or just on the right side, and finally we could have a subtyping relationship with no self-type at all.